Welcome back. The next experiment that we are going to perform is to determine the resistance of a galvanometer by half deflection method, and in the process we are going to find out something called figure of merit of the galvanometer. So the apparatus required for this experiment is we need a Weston type galvanometer. There are different types of galvanometer that are available, but the one that we will be using, which is always commonly found in practical labs, is the Weston type galvanometer. We will require a voltmeter, one battery illuminator which will act like a power source, then two resistance boxes with two one-way keys, one rheostat, one screw gauge, one meter scale, one ammeter, and of course some connecting wires. Okay. Now first thing is that how are we going to determine the resistance of a galvanometer and what is this half deflection? So to understand this, we have to go back a bit into the theory behind the working of a galvanometer, how galvanometer measures current. So like any other device, galvanometer is also based on a certain principle, and that principle is that whenever a current carrying coil is placed in a magnetic field, it will experience torque, and the torque is given by NIAB sine of theta or sine of alpha. So the torque is proportional to theta. But the way galvanometer is designed, there is two kinds of torque acting. When we pass the current, there is something called deflecting torque, and because of the construction, there is a restoring torque. And when you equate the deflecting torque and the restoring torque, you eventually get that the current that is flowing through the galvanometer is proportional to theta, which is the deflection produced by the pointer. So more current will mean more deflection. So there must be a constant of proportionality. So one can say that I must be equal to some constant k into theta. This k is called your figure of merit. So this constant of proportionality is called figure of merit. So k is basically I by theta. So its SI unit is ampere per radian. Some also write it as ampere per division. Now what is this K? So when you look at the galvanometer, you will see, depending on its design and range, there are divisions that are marked on the galvanometer. Okay? So figure of merit is defined as the amount of current that produces a deflection of one scale. So out of all the markings, whatever current will produce one scale division deflection, that much amount of current is called your figure of merit. So what are the factors on which this figure of merit depends? Well, there are different factors that we can think of. In fact, if you plot a graph of theta versus I, you expect a straight line graph, and the slope of this graph is 1 by. Okay? So how are we going to determine the figure of merit? It of course depends, it's particular to a galvanometer, it depends on number of turns, the area of the coil, the magnetic field of the radial pole, the radial magnetic field strength of the poles, and also on the torsion constant. So how do I determine it directly? There is no way to open the galvanometer and determine the number of turns, area, V and K. So that is why we have to use an indirect method by which we can determine this value. For that, we will be requiring the resistance of the galvanometer. So for that, let us see what exactly is this process of half deflection method. So imagine the circuit. Suppose there is a cell, there is a resistance box, galvanometer, of course key is there. So this key, this is key. And I will denote the resistance of the galvanometer by G. So first let us understand how much is the maximum current that gives you the full scale difflection. So imagine if Ig amount of current flows through the galvanometer, then it will produce a full scale deflection. Okay? So Ig can also be written as n into k, where n is the number of divisions. Okay, where Ig is the current that produces full scale deflection. Okay? So how do I determine this? For this we have to use a modified circuit, a little bit of improvisation is required, and that circuit is already shown here in this particular circuit diagram. I'll explain how we can determine the galvanometer's resistance, and hence from there I can determine the value of K. So let's see. Now when I close key K1, suppose K1 is closed, then a current will flow. Okay, so how much current will flow? So current in circuit will be given by I, which is equal to E divided by R plus G, because the total resistance in the circuit will be the resistance of the resistance box here, and the resistance of the galvanometer. So the current flowing in the circuit will be E by R plus G. And this is what produces some deflection theta. So I will call this current as K into theta. Let this be equation 1. Okay. And in the meantime, this K2 is open. We have not yet closed K2. Now we all know that current is proportional to K theta. So that is why I have plugged in this value. I have written this value. The simple reason being that galvanometer, the scale is linear, the current is directly proportional to theta. So now what we will do is, we will now close K2. When you close K2, you try to adjust the S. You try to adjust the shunt resistance here. It will be in the form of a rheostat. So where you can adjust S to get what? You had got a deflection theta. Now you will try to get a deflection half of theta. Okay. So that is why the name of the process is called half deflection method. So whatever deflection we had got in the first case, we will try to obtain half of the deflection in the next case when K2 is closed by adjusting the value of S. Okay. So S is adjusted to obtain how much deflection? Theta by 2. But now how much is the current flowing in the circuit? Now with the circuit having S, the resistance S will now come into the circuit. So when K2 is closed, suppose I prime is the current that is flowing. Now how much will be I prime? I prime will be given by E divided by R plus Gs by G plus S. Now why did I write this? Because now this S and this G, they are in parallel. So the equivalent resistance of G and S is Gs by G plus S, and R is in series with this both of them. So the overall resistance is R plus Gs by G plus S, which I can always write as R into G plus E into G plus S divided by R into G plus S plus Gs. Agree? So this is the current that is drawn. But how much current is flowing through the galvanometer? The entire current will not flow through the galvanometer. A fraction of the current will flow through the galvanometer. And how much current am I expecting? Suppose I expect current I1 prime. So I1 prime is the current that flows through the galvanometer. So how much current will flow? It will be a fraction of I prime. And how do I always find out the current in a resistor? We divide by, because current gets divided depending on the resistance. So I1 prime will be, how much fraction of I prime? It will be S by G plus S. If I would have wanted to find out how much is the current flowing through S, I would have got G by G plus S, but I want the current flowing through G, so it is S by G plus S into I prime. And how much is that? This is equal to E into G plus S by R into G plus S plus Gs whole into S by G plus S. And you can see G plus S gets cancelled. So I am left with Es divided by R into G plus S plus Gs. And this much current is expected to produce how much deflection? Theta by 2. So I1 prime should be K times theta by 2. Previously, I was giving theta deflection, I1 prime will give deflection half of theta. So K theta by 2. So that essentially means Es by R into G plus S plus Gs is K into theta by 2. Let this be, or that means I can simplify it that K theta is 2 times Es divided by R into G plus S plus Gs. Now look at this equation. Let it be equation 2. Look at these two equations. The first equation at K theta is equal to I, which is E by R plus G, and here K theta is 2 Es by R into G plus S. So if I equate 1 and 2, so from 1 and 2, what do I get? E divided by R plus G is 2 Es divided by R into G plus S plus Gs. E gets cancelled, and I will leave that as an exercise for you, that the value of G effectively will be how much? It will be R into S by R minus S. So this gives me the resistance of the galvanometer. R is something I decided, S is something that I adjusted to get theta by 2. So from here I get the value of G. So once I get the value of G, now it is very easy for me to determine the value of K. So all I need to do is plug in the value of G here to determine the value of K. So that is how, so finally you can write down the value of K to be E by R plus G into theta you already know, G you have already determined, so K value is E by R plus G. So this is how you can, theoretically this is the premise. Next thing that you will see is how to actually do it in an experiment. That will be shown by. Thank you so much.
Now you are going to explain and the resistance of the development and to calculate figure of it. So now this is the circuit diagram as it is shown. the circuit diagram for resistance and figure of it. Let us check with our connection. As it is shown in the diagram, battery alimenter, high resistance box, galvanometer, key all connected in series, and a some resistance box, small resistance box in key is connected parallel to the galvanometer. First of all, we have to find the resistance of the galvanometer. Using the formula G is equal to Rs by R minus S, and calculate that is amount of current required for 1 division reflection of the galvanometer, that is equal to E by R plus J into theta. So once we know R and G, we can calculate K. The observation table is shown there on the board. Observation table is here. First, what we have to do? First, we need to go to this code. Let it be K1 in the C circuit. And in the parallel position, like some resistance is connected parallel to the galvanometer, let this be key K2. First, we will keep both these key open, because if you without applying the high resistance, if you put the key, immediately a lot of current will flow to the galvanometer, which will show high end deflection. So there is a chance of getting damage. The galvanometer may get damaged. That's why we have to apply high resistance in the resistance box. Then only we will put the key here. Let us say, let me apply 2000 ohm resistance in the resistance box. Then I will put the key here. Here we find the division of deflection. Now in case of galvanometer, there are 30 divisions on both sides. 30 divisions towards right, 30 divisions towards left. We will count how many divisions of deflection are shown when the key is replaced here in the 2000 ohm resistance. Now we count, it is a 20 division deflection. So as it is a green number deflection, 20 is a green number. So here we will know the resistance from the resistance box is 2000 ohm and deflection in the galvanometer is 20. One number of divisions of deflection in the galvanometer 20. Then we put the sun key and we will apply some resistance. Let it be some resistance, maybe suppose 0.5 ohm. And let us check what should be the actually it should be the some resistance to be chosen so that the deflection will be reduced to initially we tested 1000 ohm resistance, it was showing 20 divisions deflection. So our aim is to choose certain resistance from the some resistance so that the deflection will be reduced to half, means it will show 10 division deflection. So initially I have taken out 50 on the 12 meter. With 50 it shows 9 division deflection. Then let me take 20, it shows 10 division deflection. Now resistance from the some resistance is 50 plus 20, 70 ohm. So some resistance S is 70. So we will mention here some resistance 70 and some resistance 70 ohm and division of deflection. Half deflection is theta by 2. Theta by 2, that is 10 division deflection in the galvanometer. Then you will put the values of R, S, R minus S. We find G. Once we find G, then we can calculate figure of merit K. Figure of merit K is equal to E by R plus 3 into theta. EMF of the battery element is 2 volt. R, we have to use resistance 2000 ohm. R plus G. G already is calculated here. Previous column. E by R plus G into theta. Theta is the deflection. 20. So substituting that value, we will find K. One after the other over. Next observation. So every time you have to you will go on having the resistance from the resistance box. So that here the division deflection will be different. Now replace the sum, one observation over, replace the sum key deflection now? It is coming. We will try 1000 also. We will try 1000. It is going out of scale. So we cannot choose 1000 as the division of deflection is beyond the scale. So then we will use like 500, 1500, let me see. Okay. With 1500, now the division of deflection is now 25, 26, 27. As 27 is not a even number, we have to take even number deflection. As the division of deflection is 27, we have to apply to more resistance relatively on thread. Now it is also coming 25. Now it is a trial method. No one trying with some resistance so that the deflection will be even number deflection. Remember even number deflection. It is okay. Now it says 24 division deflection. As you check, it is showing 24 division deflection, whereas resistance shown is 1000 plus 500 plus 200. That is 1700 ohm. Resistance showing 1700 ohm. Deflection in the galvanometer is 24. To be noted here, 1700 ohm. Then division of deflection 24. Then we will put some resistance, some key here, and choose some resistance. Let it be same 70, and deflection is reduced to half, that is 12. So S is 70, half deflection again 12. Over again use the formula, calculate G, using G, R and theta, calculate K. So similarly, we have to take C6 observations. Total at least 6 observations we have to take to calculate the galvanometer resistance and also to calculate figure of it. What is their aim? Why do we find galvanometer resistance and figure of merit? Actually, this galvanometer resistance and figure of merit is used to convert the galvanometer to a voltmeter and ammeter. If you want, you can convert the galvanometer to voltmeter by connecting a high resistance in series with the galvanometer, so that the galvanometer will be converted to a voltmeter. Similarly, a galvanometer can be converted to ammeter by connecting a very small resistance in parallel with the galvanometer. So for that reason, we need to find the galvanometer resistance and figure of merit. For galvanometer resistance, for converting galvanometer to voltmeter, resistance required is B is equivalent to R. The resistance required is equal to R, B is equivalent to resistance which will be connected in series with the galvanometer. R is equivalent to V by Ig minus G. B is the range of the voltmeter which is to be designed. Ig is the maximum current required for full scale deflection. That is, Ig is equivalent to N into K. Figure of merit minus G. That is the galvanometer resistance. So anyway, this galvanometer resistance and figure of merit is used for conversion of galvanometer to voltmeter. Similarly, this galvanometer can be converted to ammeter using a very small resistance in parallel, using the formula Ig by I minus G, where Ig is equivalent to maximum current required for full scale deflection, G galvanometer resistance, and N is number of divisions on the galvanometer. Then you will calculate a small resistance. The resistance which will come is of the order of 0.002 ohm or something. Very small resistance which will be connected in parallel with the galvanometer, so that the galvanometer will be converted to ammeter. Anyway, we are not going to do those experiments. So only you know that that is the use of galvanometer resistance and figure of merit, which we are calculating. And the questions are almost same as in previous experimental arrangement. Connection should be tight, neat and clean. This should be tightly closed. And always before starting, both the keys should be open. A high resistance will be applied, then only key1 will be raised. Otherwise, the galvanometer will be damaged. There will be higher reflection. That's it.